Hello and welcome to the module 5 of the computational techniques course. What module 5 is going to cover is essentially what is known as regression and interpolation. We have perhaps encountered regression right in our high schools when we started looking at how to fit a straight line to a bunch of data points, and we have done this regression fair number of times. For example, you have several number of data points and we need to find out the best fit line that passes through these data points. That is what is known as linear regression. Interpolation is another thing, again what we would have done earlier as well. Essentially you are given some amount of data, say n number of data points, so those represent discrete data points in a continuous set. So if we want the value at any other point between these amongst these n data points, any other point other than these n data points, we will have to use interpolation. In this particular module is go through an overview of where regression and interpolation are going to be used in chemical engineering systems, and then we will look at several ways of doing this regression, and then we will continue with several ways of doing interpolation. Each method has its own advantages or disadvantages, or rather more appropriately it has a range of applications where you could use that particular method. Okay, so let us look at an example. Let us say we have been given the following data. X is the independent variable and y is the dependent variable, and we need to find out a functional correlationship between the independent variable y, how this particular y relates to this particular x, and this is just the data that is given to us. For example, one example could be how the rainfall in the city of Chennai relates to say the temperature that we find, or relates to the relative humidity and temperature and things like that. So just we have an independent variable x, we have a dependent variable y, and we want to find out a functional relationship between x and y. That is what regression is going to be about. So what we have done over here is plotted this y against x, and these are the 6 data points. Regression in this particular example is a means to obtain a straight line that best fits the data. In general, the regression we may not necessarily be interested in fitting straight lines, we might be interested in fitting some functional forms to the given data, but in this for motivating examples in the beginning, we will just look at fitting straight lines to the data. Now let us look at interpolation case. Interpolation, again we have been given the same data as before, and we have plotted the data as before. What interpolation, the question we ask in interpolation, for example, is given this data, let us say I want the value at x equal to 2. So let us say value at x equal to 2, how do I get that particular value? So in a way interpolation is like joining the dots. It is basically trying to find a curve that passes exactly through all of these points that we have shown over here. If we look at the previous slide and see what we did with regression, the curve did not necessarily pass through all the data points, right. So for example, none of these data points actually this best fit curves passes through. It is just a curve that is going to minimize some kind of an error or some kind of a distance between this point and the straight line. Okay, that is what we do in regression. On the other hand, in interpolation we will get a straight line, we will get a curve that passes through all the data points that we have. So if we want to find out the value at this particular location, we just get this value by reading off from the curve, substituting x equal to 2 in the equation of the curve, and we will get the interpolated value at x equal to 2, we will get the value of y. Okay, let us compare regression and interpolation in this particular case. Specifically what I have done is I have fitted a best fit straight line to these data points, and in this particular example I have fitted what is known as spline interpolation. both of which we are going to cover in due course in this particular module. So in regression we fit the chosen function to the data. In this particular case it is a straight line, and the equation of the straight line is y equal to 0.45 plus 0.47 x. In case of interpolation, if given a finite amount of data, we are interested in obtaining new data points within the range. Again, within the range is a very important term over here, because since the data coverage is between 0.8 and 4.9, we will be able to interpolate only within these data points. We will not be able to extrapolate beyond any of these data points. So what interpolation does is, within these data points, you can, if we are interested in finding the value of the independent variable y given a particular dependent variable x, we can find that particular value. For example, if we have x equal to 2, y will be 1.87. so this particular point is about 2 comma 1.87. okay, that is what we do in interpolation. Okay. Now let us look at examples where regression and interpolation are used, and again these are examples, these are simple examples, these are examples which you would have done in some of your courses earlier. For example, we have this rate expression, it is a first order rate expression in which the rate depends on the temperature as well as concentration of species A. So if we carry out this reaction in a batch reactor or say in a continuous reactor, and we do that, we run that reaction for certain amount of time and try to figure out the conversions. From the conversion that we can get the rate, which is essentially going to be the slope of the conversions right in the right at the start of this particular experiment. So once we have this rate of reaction R and the temperature T, basically what we can do is we can then take a logarithm of this particular function, and when we take the logarithm of this function, we will be able to get the k value. K value is nothing but k0 e to the power minus e by RT, and the logarithm of that will get us log of k0 and e by r multiplied by minus 1 by t. So now if we plot log of r as the y axis and minus 1 by t on the x axis, what we will essentially get is, or rather what we should get if this particular functional form is correct, is a straight line that passes through the data that we have over here. The intercept of this straight line is nothing but log of k0, and slope of this line is essentially e by r. Okay. So this is an example that we have studied much earlier while talking about, finding out rate expression in chemistry courses and things like that. What we are interested in doing is formalizing the ways in order to get the best line that passes through these points, and we are going to look at a formulation which is not only going to be finding straight line through y versus x type of data, but when we have multidimensional data as well. In that particular case, how do we get the straight line or any kind of a functional curve passing through the data. Okay. So what we have over here is an inherently, it is a non-linear function, and we use some transformation. For example, here a logarithm we take in order to transform a non-linear problem into a linear problem, and then we can go ahead and do the regression for this linear regression for this particular example. Okay. The next example would be interpolation, and the viscosity of lubricant oil, for example, will be measured at various different temperatures, but sometimes the value of the lubricant may not be available at the temperature of our interest, and if that is the case, we might need to use interpolation in order to find out at that particular temperature what the viscosity of oil is. So just to look at the example, the data that we had previously, this is not the viscosity data, this is just the same data that we had previously. What we can do is essentially fit all these data, fit a specific type of curves through these data points, and one example would be to fit straight lines between each subsequent each successive data point. So you have a straight line joining this point and this point, you have another straight line joining this point and this point, you have a third straight line joining this points, fourth one and fifth one. So what we have over here is 6 data points give us essentially 5 intervals, and for each of these intervals we fit one straight line that goes through all of and the final curve will eventually go through all of these data points, but this curve that we get finally is composed of 5 independent straight lines. Okay, so that is one way of doing this interpolation. The other possibility is what is known as spline interpolation, and spline interpolation for example will fit a curve to each of the subsequent data points, and that final curve is going to be what is the interpolating curve from where we can get the data in addition to all of these 6 data points. So for example, the value at x equal to 2 was 1.87, so that was just read off from this particular curve. Okay, so that is the difference between essentially interpolation and regression. So let us now formalize the way of dealing with this interpolation and regression. So we have some set of data, 6 data points in this particular case. So let x be an independent variable and let y be a dependent variable, and we have been given capital N number of data points. In this particular case n was 6, so we have been given x1 y1 x2 y2 up to xn yn. We want to find out a best fit curve in some way or the other, and that curve is given by y equal to f of x semicolon theta, where theta is the set of parameters. So this is a functional form of that particular curve. Okay, so the model we will write as y equal to f of x comma theta. So that is our x semicolon theta. So that is the model we are interested in. We are interested in finding the values of theta that will in some ways best fit give a best fit for y equal to f of x curve. The actual data again to recap consists of x1 y1 x2 y2 and so on up to xn yn. The prediction is going to be, now let us say we assume certain value of theta. Okay, so we decide on a function, we assume certain value of theta. Once we substitute the value of x, we will get certain value of the dependent variable y. We call this particular value of dependent variable y with a hat. The hat represents that it is a prediction. Okay, keep in mind that this is the model, whereas this is the prediction from the model. So what we have done is we have substituted xi over here and we will get the value of yi. Now because there is an error, for example if we look at if we look at this particular curve, so this particular value, the x coordinate is xi and the y coordinate for this value is yi. So if you substitute basically xi into this particular equation of this particular straight line, we will get the value of y which we obtained from the function at this particular point, which is actually different from the actual data that we had. So this data point will be called y, whereas this particular predicted value will be called y hat. Okay, so we have written the prediction equation in the form yi hat equal to f of xi comma semicolon theta. Now there is an error, as we showed in the previous graph, there is an error between the true data value and the value that is obtained through the model, and this error is essentially we will write that as e subscript I, and we just take yi onto the other side, we will get yi hat onto the other side, we will get yi, which is the true value from the data is going to be equal to f of xi comma theta, which is nothing but the model prediction of yi plus the error between the true yi and the model prediction. Okay. And what we are interested in doing is we are interested in finding out methods that will minimize these errors. Okay. Before going further, we will also just define a few terms from statistics. The mean of data is nothing but sum of that data divided by the total number of data points. It is something that we are all familiar with. This is essentially the variance of the data. Variance of data is nothing but square of the standard deviation, which is which essentially gives us how the data is spread with respect to the mean x bar. So how much is the spread of xi with respect to x bar is what is given by the variance, and sigma is the square root of variance is nothing but the standard deviation. Okay. So again, to how is interpolation and how are interpolation and regression going to be different from each other. In regression, what we do is we will choose a functional form f of x. Now how do we choose the functional form f of x? For example, in the Arrhenius rate kinetics, the functional form we chose for the functional form we chose for the rate of reaction r was nothing but k multiplied by Ca, and for the rate constant k it was k naught, which is a frequency factor multiplied by e to the power minus e by RT. Okay. That is how we chose the functional form of x. For a given value of theta, we obtain the yi hat, which is the model prediction, and we recursively use some method or we use some kind of a direct method to find out the theta which minimizes some norm of the error in some way. So this could be the absolute value of the error, sum of the absolute value of the error, or it could be the sum of square of error, and so on and so forth. That is what is going to be our objective, is to find out theta that will minimize the error in some form. As against that, in interpolation case, we do not have to choose a functional form. There are several standard functional forms that exist, and based on the method that we are going to use, we will use one of those standard functional forms for interpolation. Interpolating function passes through all the data points, which means that the error is going to be 0 for each of the data points, and the usefulness of interpolation is to fill in the data at new x values, whereas the use of regression is to get a closed functional form that can then be used for various purposes. For example, the rate of reaction can be used in order to design a CSTR or a PFR and so on. Okay. That is the difference between and the salient features of using regression and interpolation. Okay. So after we look at, so initially we will look at a single variable case, that means the output is one variable and the input is a single variable. Next we will extend that particular example to a multivariate case where x1 to xn are small n number of variables and capital N is the total number of data points. So we have the data in the form x1 to xn at data 1 comma y1, x1 to xn at data 2 comma y2, so on and so forth from x1 to xn at data n and yn. So this is what our data would be, and our objective in multivariable case will be to obtain theta, which is going to be a vectorial theta that will give us the best fit for a curve y equal to f of x. Okay. An example of multivariable case is to find the specific heat as a function of temperature. if you go to the NASA's website, there is NASA polynomial form of specific heats of several gases, and this has been taken from that particular NASA polynomial fit. The specific heat of methane, the constant pressure specific heat of methane is given by this particular quadratic function is A0 plus A1T plus A2T square, whereas A0 is 85.8, so on and so forth. So what we have over here is we are trying to fit a specific function in order to functional form to the data Cp versus T, and as we will show later on in this particular module, this is an example of linear regression. Another example is a functional regression where we want to fit a functional form of this type. This is an Antoine vapor pressure relationship. Log of the saturation pressure is a function of the temperature, and A, B and C are the three constants in this particular equation. This particular equation as it is formulated is going to require nonlinear regression. Of course there is an alternative way of formulating this problem also, which is going to result in linear regression. Okay, we will look into that as well, how to do nonlinear regression or functional regression or polynomial regression in this particular module. Okay, so to just recap the overall methods that we are going to use in this particular course. First we will talk about linear regression in one variable. After that we will go on to linear regression in multivariables, also known as multilinear regression, followed by polynomial regression. We will then analyze these regression methods and look at the extension, and then finally look at the nonlinear regression. So this is the regression part of the course. The linear regression is nothing but fitting the curve y equal to mx plus c to the x versus y data, but it is actually more than that, because for example we have seen in one of the earlier slides is we can actually fit a straight line after we do some kind of transformation to the original function of this type. Okay, so although linear regression per se in a single variable case is fitting a straight line to x versus y data, it is an immensely useful way of doing regression. The next we will look at is extension to the multi regression case, which is again similar to what we had talked about earlier, is if y is not just a function of x but a function of multiple variables. Okay, so that is the overall outline for regression. After finishing off regression, we will then go on to interpolation. We will look at polynomial fitting. Basically what we will say is some of the ideas that we learn from the regression part of this particular module, whether we can apply the same idea to the interpolation part, and we will see that we run into certain problems when we try to do this, to do polynomial fitting for in order to get an interpolating polynomial. So there are alternatives in order to do this interpolation and get rid of some of these limitations, and specific methods that we are going to look at is Lagrange's interpolating polynomial and Newton's methods, and finally we will finish off with spline interpolation. Okay, so that is the overall overview of or outline of what we are going to cover in this particular module. After doing an overview of what we are going to cover in this regression and interpolation module, we will now just go and look at the linear interpolation case in single variable and derive the equations how we can get the values of the slope and the value of the intercept for the single variable case. Again for we have our data x1 y1 x2 y2 and so on up to xn yn. We want to fit a functional form, or the model form is going to be y equal to a0 plus a1x. A1 is nothing but the slope and a0 is nothing but the y intercept for this particular curve. So, this is the model that we are interested in fitting. When we substitute the value of xi in this particular equation, the value that we will get from the model is, we are going to call it yi hat. Yi hat is going to be a0 plus a1 times xi. For example, let us consider this particular data point. Let us say x1 value was 0.2 and y1 value was 0.3. So, if we substitute the x1 value of 0.2 and given the values of a0, so what I am saying is x1 is 0.2, y1 is let us say 0.3, and the functional form over here was let us say 0.5 minus say 1 times x. If this was let us say the functional form, then substituting x equal to xi, we will get 0.5 minus 1 into 0.3, that is 0.2, which is equal to 0.3, which is exactly the same as y1 that we had earlier. But instead, let us say instead of this, let us say the y1 was 0.29, okay. In that case, when we substitute the values of x1 in this particular equation, we will get y1 hat is going to be equal to 0.5 minus 1 into 0.2, which we just obtained as 0.3, which is different from the y1 hat is different from y1. This y1 is data, this y1 hat is the model prediction, okay. So, the error ei is the difference y1 multiplied by y1 hat, okay. And in this example, that the error is minus 0.01, okay. That is the error in between the data and the model prediction of that particular data, okay. Previously, when we had taken x1 and y1 as 0.2 and 0.3, error E1 was exactly equal to 0. In general, we need not always get the error to be exactly equal to 0. So, we are going to look at a general case where the error is going to be certain value ei, okay. So, yi equal to a0 plus a1 xi is, as we had said earlier, the model prediction, okay. So, the error is yi minus a0 minus a1 xi, that is the error for ith point. You will have an error for first point, second point, and so on up to all the end points, okay. So, as we had before, let us look at the 6 data points that we had. We had 6 data points, something like this, okay. So, what let us say a given value of for a given value of a0 and a1, we will get a straight line as shown over here. This clearly is not going to be the best fit line. The best fit line is perhaps going to be something like this. The dotted line is perhaps going to be the best fit line, but let us say this is the particular line that we have right now. in that case, let us look at graphically what the error EI really means. I will just erase the dotted line that I had drawn. Okay. So let us look at the fourth point. For the fourth point, basically this is the value xi, this particular value is yi hat. Yi hat is the value that we obtained from the model prediction, that is by substituting the value of xi in the equation of that straight line, and yi is the actual data. Okay. So this particular vertical distance is the EI. Okay. So what we have is essentially for each of the data points we have this vertical distance as E1, E2, E3, E4, E5 and E6. Okay. So the objective of any kind of regression technique is going to be, for the regression technique will choose to minimize the error in some form. Okay. And the way we have learnt in so far, the way that the thing that works the best with respect to minimization essentially is to minimize the square of error. Okay. So if you have to minimize the square of error, okay. So what we want to do is we want to find A0 and A1 such that okay. So this is essentially our problem statement, is we want to find the values of A0 and A1 such that the sum of square of errors in the data and the model prediction of that data is minimized. Okay. So let us substitute the form that we had for EI in this particular equation. So we will get forgot the summation sign over here, summation I equal to 1 to n yi minus A0 minus A1 xi the whole squared. Okay. So this particular term, if we look at within the summation sign, this particular term is going to expand as yi squared plus A0 squared plus A1 x1 A1 xi the whole squared, okay, multiplied by 2 times this term and this term with a negative sign, multiplied by 2 times this term multiplied by this term with a negative sign, multiplied by 2 times this and this term with a positive sign, because there are 2 negative signs which cancel off. Okay. So this particular term can be expanded as yi squared plus A0 squared plus A1 squared xi squared minus 2 times yi times A0 minus 2 times yi A1 xi plus 2 times A0 A1 xi, summation I equal to 1 to n minimize A0 A1. Okay. Now how do we find the value of a1, a0 and a1 that minimizes this particular function? So let us just look at the equivalent problem. To find some x that minimizes g of x, the x that minimizes the g of x, we are going to take dg by dx, the slope, and equate it to 0. Okay, this will give us either the minima or the maxima for this particular g of this particular value g of x. Okay, so in this particular case, since it is a function of two variables, we want to find out this particular guy over here, differentiate it, take a partial differentiation with respect to a0 and equate it to 0, and take a partial differentiation with respect to a1 and equate it to 0. It is the same problem as we had stated over here. Since this is sum of square of errors, we will write this as SE, and our problem is to minimize or to find a0 and a1 that is going to minimize SE. Okay, as we just said less than a minute back, the way we are going to do this is to take partial differentiation of SE with respect to a0 and equate it to 0, take a partial differentiation of SE with respect to a1 and equate it to 0. What we mean by partial differentiation with respect to a0 means that we hold a1 constant and differentiate the overall equation. In this case, we hold a0 constant and differentiate the overall equation. Okay, keep in mind, in this particular problem, x1, y1, x2, y2 and so on up to xn, yn are data that have been given. Since it is data that have been given, those for the purpose of differentiation have to be treated as constants. So this is a constant term for the purpose of differentiation. This term depends on a0, this does not depend on a0, so d by dA0 of this term will be 0, so on and so forth. So now we start differentiating this term. Now keep in mind that differentiation operator essentially is a linear operator, so you can take the operator within the summation sign. So what we will do is we will keep the summation sign outside, summation I equal to 1 to n. Okay, and let us look at this particular expression over here. Now we are differentiating with respect to a0, so this term will go away, there will be 2 times a0 term, this will go away, 2 times yi term, 2 times yi a1 xi, this will again go away because there is no a0 over here, and there will be 2 times a1 xi term. Okay, so the terms that we will retain in our in dSE by dA0 are these 3 terms. Okay, so this particular term is going to be 2 times a0, the second term is going to be 2 times yi when we differentiate with respect to a0, so minus 2 times yi, and the third term that we have over here is going to be 2 times a1 xi. Equal to 0, and we can cancel off these 2's over here. So that will be our first equation. So our first equation is going to be, now a0 is a value which can be taken out of this summation sign, because a0 is one particular value for while we are trying to do this summation. So this a0 summation I equal to 1 to n of 1 is going to lead us to a0 multiplied by n minus summation of yi I equal to 1 to n, plus we take a1 out of the summation. So, we will have a1 summation of xi is going to be equal to 0. So, that is the first equation. What we will do is we will take summation yi onto the other side and retain the terms in a0 and a1 on to the left hand side. So, we will take summation yi onto the other side, and we are summing over from I equal to 1 to n. Okay. So, this is going to be our first equation. Now, let us look at the second equation. The second equation is going to be obtained by differentiating SE with respect to a1. Again, this particular term is going to vanish away. This will be retained, and this will be 2 times a1 times xi squared. This term is going to vanish because there is no a1 term over here. This is going to be retained, and this term is going to be retained. So, again we will have, like before, we will have 3 terms that get retained. Okay. So, the first term that is retained is 2. So, let's look at yeah. So, in this particular term we will have 2 times a1 times summation of x1 squared. So, we have again this summation I equal to 1 to n outside, and in there we will have 2 times a1 multiplied by xi squared. Okay. The second term is minus 2 times yi xi. Okay. And the third term is going to be plus 2 times a0 xi. We are differentiating this term with respect to a1, so we will have 2 times a0 xi. Equals 0, and again we will discard these 2's. So, we will have we will rearrange it again, so that a0 is our first term, a1 becomes our second term, and so on. So, we will have some a0 times summation of xi I going from 1 to n. Okay. The second term is going to be plus a1 summation I equal to 1 to n of xi squared. Okay. And what we do over here is we will take the xi yi term on to the right hand side. So, that is going to be equal to summation xi yi I equal to 1 to n. Okay. So, now what we have is we have 2 equations in 2 unknowns. The 2 unknowns are our a0 and our a1. These are the two unknowns, and we have 2 equations, and then we can solve these 2 equations. We can solve this equation by, so in this particular equation we will multiply by summation of xi, and this equation will multiply by n. So, multiplication by n, I will write that using a different colored chalk. So, we multiply this entire equation by n, and we will get n times a0 times this plus this equal to n times this, and then in this particular equation we will multiply by summation of xi. So, we will multiply this by summation of xi, okay, and this particular also we will have this multiplied by summation of xi. Okay. So, now what we will do is this equation minus this equation will lead us so this and this term will vanish away. We will have a1 multiplied by summation xi multiplied by summation xi minus n times summation xi squared will be equal to summation xi multiplied by summation yi minus n times summation xi yi. Okay. So, this will lead us to A1 is going to be equal to summation xi multiplied by summation yi minus n times summation xi yi divided by summation xi minus n times summation xi squared. And there is that n term over there. Okay. So, this is going to be our A1. Okay. And we can use this particular equation to get our A0. So, our A0 n times A0 is going to be, so just ignore this yellow terms over here, because remember this yellow terms had come because we had multiplied this entire equation with summation xi. So, ignoring this yellow terms, what you will get is summation of yi minus A1 times summation of xi is going to be equal to n times A0. So, we have summation yi minus A1 times summation of xi, okay, and now you divide throughout by n, we will have summation of yi divided by n minus A1 times summation of xi divided by n. If you recognize this, this is nothing but average of xi and this is nothing but average of yi. So, A0 is going to be equal to yi avg minus A1 times, sorry, not yi avg, y avg minus A1 times x avg. Okay. So, this is how we will get the value of A0, this is how we will get the value of A1. Okay. So, given n data points x1 y1 x2 y2 up to xn yn, we first find out summation of xi, we next find out summation of yi, we find out summation of xi times yi and summation of xi squared. Okay. The difference between, for example, this term and this term is that we square the xi's first and then sum them up, whereas in this particular case we get summation of xi and then square up that particular summation of xi. Okay. So, for example, if we have the value of xi as say 1, 2 and 3, okay, then summation of xi squared, the whole squared is going to be 1 plus 2 plus 3, that is 6 squared, that is 36, that is essentially this particular term, whereas this term is going to be 1 squared plus 2 squared plus 3 squared, that is 1 plus 4 plus 9, that is 14. Okay. So, this particular guy is going to be 14, whereas this particular guy is going to be 36. Okay, so that is the difference between summation xi the whole squared and summation of xi squared. Same difference over here also, we find the summation of xi, we find independently the summation of yi and multiply the two minus the summation of the product xi yi. So x1 y1 plus x2 y2 plus x3 y3 so on and so forth is what this term essentially indicates. Okay. So that is what we have for today for linear regression. What we will do in the next class is going to be to extend this linear regression in one variable to a linear regression in multiple variables. So not just not just the data x versus y, but we have multiple independent variables, then how to do the linear regression. Before we do that, we will take Microsoft Excel and show an example, the same example that we saw in our PowerPoint slides. We will take that same example in order to get the values of A0 and A1, and then we will find out an alternative which and a more general way of doing this linear regression, and then talk about linear regression for functional forms such as polynomial regression or functional regression. That is what essentially we will be doing in the next lecture. Okay, thank you.